Okay, first of all, I would like to thank you for coming so early and attending my talk. I would also really like to thank the organizers of the event. It's a great honor for me to be here and be invited. Today, I'm going to be talking about feature selection. And this is a workshop in causality, so there must be some kind of connection. And so one of the things I'm going to do today is explore these connections between causal discovery, causal modeling, and at the same time, feature selection. Now, feature selection is a general problem, and I'm guessing that some people in the audience may not necessarily be have an extensive background in causality, so I'll try to explain some basics in this talk. The messages, the key points that I'm going to argue today are the following. First of all, that feature selection is arguably the main tool for knowledge discovery when we use analytics. Okay, it's not so much to find, sometimes the goal is not to find necessarily the most predictive model. Sometimes the goal is feature selection itself, and that's why we study it. Secondly, that causal models and causal discovery theory and algorithms really help us understand the problem of feature selection. Okay, and hopefully this is going to become evident. And they do so in a non-parametric way without specific assumptions like linearity or Gaussianity or something like that. And eventually this understanding leads to algorithms inspired by this theory that provide theoretical guarantees that are applicable to almost any type of data for which we have a conditional dependence test available. I'm going to show results that can make the algorithm scale to tens of data sets with tens of millions of features and tens of millions of rows or instances, big volume data. They have competitive predictive performance against alternatives. One prominent alternative is the lasso or lasso, whatever, I don't know how you pronounce it exactly. And they can find, with recent extensions, we actually study how we can find multiple solutions to the feature selection problem. Another nice thing about these algorithms is that they have an intuitive causal interpretation. So we know essentially the causal relationship of the variables we're going to select. And at least we offer robust and efficient implementations in R. Okay, now let's start with the problem itself, and then we'll see the connections with causality. So generally, what we do is we take our training data in the form of a two-dimensional matrix, at least in the simple case. We apply a learning method like a decision tree, and we learn a classification model. And for some reasons, we would like to interject an algorithm there that selects some of the columns, that selects some of the features. Sometimes I will refer to them as interchangeably as variables, observed quantities, attributes, depends your terminology and what your background is. And of course, this feature selection, we expect, if it's reasonable, to only maintain the columns that carry all the information that we need to predict the target variable t. Okay. So why would we like to do this? Well, in computer science, usually people expect that they're going to apply feature selection to increase predictive performance. How can this be? To throw away features and get better performance? Well, sometimes it facilitates the task of the classifier if we throw away noisy or irrelevant features, of course. But I argue that this is not why most people in most analytics tasks do feature selection. When you work with a medical doctor, for example, they may not care on a classification model for a cancerous tissue or not. They can actually take the tissue and look in the microscope. What they care about is what are the genes that make the difference, that carry the information. So a lot of the times, in my experience, feature selection is the primary goal of the analysis, and the predictive model is actually a byproduct. Because it gives us intuition about what matters. And this is not an accident because we're connected to the causal mechanisms that generate the data. Now, you can use other methods like dimensionality reduction if you want, for example, to remove noise but you don't get interpretable results. Okay, so a major concept that we're going to use for feature selection algorithms is the independence and dependence and conditional dependence and independence. So let's see these concepts. So the color of the teeth, let's say we measure the color of the teeth and the nicotine levels in a bunch of people represented by dots in these graphs. And does this give us information to predict the nicotine levels? Well, of course, because if we know the column, we know better what the average is and we can make a better prediction. But what about if we're given additional information? What about if we're given whether you're a blue dot or a red dot corresponding to smokers or non-smokers? Well, now, if you know the color, whether you're blue or red, then me telling you the color of your teeth and which column you are does not change your prediction, doesn't change the averages, doesn't change the distribution of nicotine levels. So this quantity, the column, the color of the teeth, becomes dependent with the nicotine levels, and it becomes conditionally independent once you know something additional. All right. So the condition here is this one. We will call yellow teeth independent of the nicotine levels given smoking if once we know smoking and then we add this additional variable, it doesn't change our conditional distribution of the nicotine levels. And this is the notation I'm going to use. So here's an example where two quantities are dependent and then they become independent. Okay, the opposite can also happen. So if they ask you to predict the color of the dot given X, well, it seems like there's an even mix. It doesn't matter where you are or this axis to predict the color. So X doesn't provide you information about the color. And same for Y, it doesn't provide you information about the color. So if you look individually, X or Y to predict T doesn't give you information. But it could be that if you look both of them together and you plot the data on both X and Y simultaneously, that a nice pattern appears. Okay? So this is an example where two quantities that are independent, one doesn't help you predict the other. If you have some additional quantity measured, now they become very predictive. Okay? That kind of like gives intuition as to why the feature selection problem is difficult. Sometimes you have features that give you information, but if you select some other features, they're not needed. And sometimes features that seem irrelevant, if you see them in the condition on some other features, they become relevant. Okay, so this concept extends to all sorts of quantities like nominal, ordinal, time to event, and so forth. And how do we determine a conditional independency or dependency? We use 100 years of statistics that have developed all sorts of conditional independence tests. And this is the only access to the data. The access to the data is only going to be through these tests in the algorithms. And the tests return a p-value, which can roughly be interpreted without going to the mathematics. If it's a small p-value, then dependence is highly likely. And if it's a large p-value, actually we don't know, but since we need to make a decision in the algorithms, we treat it as independence. Okay, and in practice, if you try to build, to run these tests and condition on a large set, so you assume a lot of variables are known and you try to find the dependence or independence of another variable with a target, these p-values become unreliable. So the algorithms would need to condition on few variables if possible. All right, so how do we define the feature selection problem? Okay, and there's been, I think, a lot of misunderstandings about this. Hopefully, I'll clarify some issues here. So the single solution, what I call the single solution problem, I'll define it as trying to find a minimal size feature subset such that makes all other features independent of the target. Okay? So you try to select S that everything else doesn't give you additional information for T. And at the same time, S is minimal. So if you break down this independence, it means that the conditional distribution of T is given S is the same as the conditional distribution of T given all features, all right? Now, this definition assumes an oracle, it assumes we have full access to the conditional distribution of T. Okay, so it's kind of an asymptotic definition. Okay, now S also in the causal discovery world is called a Markov blanket. Also Perl calls it Markov boundary, but I'll stick with Markov blanket here. And S is a minimal size, a Markov blanket of T is a minimal size set that renders all other features independent of T, carries all the information is minimal. And this is an NP-complete problem even for simple cases like linear relationships. And there are many subtleties in this definition. I have examples here, I'll just go through the main points, that since we want something that is minimal size, the encoding of our features matters. So sometimes the observed quantities are transformed to features, and the way you transform these observed quantities and you encode them as features determines what is a solution. Another point is that whether we use minimal in the definition versus minimum. If you use minimal, then some subsets may be solutions. If you use minimum, then it could be the case that some subsets are not solutions anymore. So these are some subtle points in the definitions. Now, in practice, we need to solve this problem, obviously, without access to the full distribution of the target. So we need to approximate it from data. And how do we do that? We try to solve this problem. Maximize some performance metric of a model that we build with features S using some learner F such that S is minimal. And that actually could coincide with the asymptotic definition that I gave before. Okay? Now, again, there are many subtleties that have confused people like for a long time. One is like how we measure performance, predictive performance. For example, if you use accuracy, then you find one solution. If you use some other metric, you find another solution. Okay? And I give an example here where X is required for the probability distribution of T. You really need it for to have the independence condition, but if you try to maximize, it doesn't maximize, you don't need it to maximize accuracy. Another point is the solution depends on the learner that you use. If your learner is naive, it cannot model correctly the joint probability, the probability of T given S, then you have a problem. You may find things that look weird as solutions. Kohavi and John gave a problem where you have a constant variable, and because you, obviously you don't need it, doesn't carry any information, but because you use a really naive classifier, you need Y for optimal prediction, and that created a lot of confusion. But if one uses a learner that can actually learn the conditional distribution of T and uses a performance metric that is optimized only when the independence holds and not otherwise, then solving this problem is going asymptotically to give the asymptotic solution. All right, now what about like another key point in the feature selection problem is what about multiple solutions? And in practice, believe me, there are many multiple solutions. And this is important because, for example, when, in the medical domain that I work quite a bit, it is misleading to go to a doctor and say, it's these 5 genes that make all the difference in the world, everything else is redundant or irrelevant, when in fact there could be another 3 genes or 5 genes, whatever, that are equally good. Okay, so I define, and I think that's important to solve the multiple solutions problem where you actually try to find all minimal subsets, all Markov blankets that carry the information and are minimal. It's a much less studied problem. I list here some recent papers, and it's very related to stability of feature selection. People run feature selection, let's say, in a cross-validated fashion. Sometimes you see X, sometimes you see Y, and you say, okay, X is not stable, I throw it away, Y is not stable, I throw it away. But it could be the case that, no, you need X, but you could replace it with Y. Okay, doesn't mean you should throw it away. But I'm not going to go much into the details of this problem because there's no time. So given what I said, I give a taxonomy of features, and the features, for feature selection. One is like features that really provide no information in T, no matter what you condition on, in any context, no matter what, you see them in conjunction with other features, they never give information for T, they are irrelevant. Then we have the features that participate in all solutions. They're in all Markov blankets. I'll call them indispensable. You absolutely need them for optimal prediction. And then we have features that are in some solutions, but not in all solutions. So you could actually, you need them for optimal solution, but you could replace them with something else. So I call them replaceable. And they will not be stable if you actually run the algorithm many times, an algorithm that gives you only one solution many times. And if they're not irrelevant or indispensable or replaceable, meaning that they provide information, but you don't need them in any minimal set, they are redundant. There's a previous classification by Kohavi and John to irrelevant, weakly irrelevant, strongly irrelevant, and it coincides with this only when there's a single solution. If there are multiple solutions, then this taxonomy is not good. Okay, so this is, in my opinion, how we can define feature selection problem. Now let's go to causal models. And probably for a lot of people in the audience, this is going to be trivial, but as I said, like people who do feature selection need some background in the causal models to understand the rest of my talk. So I'll deal with Bayesian networks, causal Bayesian networks here, which are graphs and probability distributions connected by some condition. We'll see about that. So the graph expresses the causal relationships between the observed variables. And we also have a joint probability distribution. And of course, something connects the two. Something must connect the two that expresses our intuition about causality. It cannot be that any graph can be joined with any probability distribution. And this condition is the causal Markov condition that states that every variable is independent of its non-descendants given its parents. Okay? And this encapsulates our intuition about what causality is. I'm not going to explain why this is the case and so forth, but it's generally accepted. And look, here it talks about independence. Okay? And in the feature selection problem, we also look for a set that makes everything else independent. So that's where the connection starts to begin. So let's see, if given this assumption, if I have this causal model, what independencies can I infer? Well, the Markov condition states every variable is independent of its non-descendants given its parents. So let's apply it to Z. Z is independent of its non-descendants. These two are non-descendants, given its parents, given X. So we have this independence. All right? That comes out from the Markov condition and the causal graph. Now, another assumption is faithfulness. It's a very key assumption for all the algorithms. That's a key assumption for all the algorithms. And it states essentially that these are the independencies that come out from, entailed from the Markov condition are the only ones. So anything else we can write in this form is a dependence. That's the assumption, all right? And now, the Markov condition directly states some independencies need to hold in your data. If this is the true causal model, you expect in your data to see this independence. But With the axioms of probabilities, in a large network, you'll have a lot of these independencies from the Markov condition, and you can use axioms of probability to prove more independencies. So it would be nice if we can actually find all independencies that are entailed. This is actually possible with what is called the d-separation criterion. It's an algorithm that determines all the independencies that we expect in our data if we know the causal graph. Okay, and it's a key algorithm to understand why the algorithms work and how we can design algorithms and the theoretical properties of the algorithms. So the d-separation criterion, first of all, defines some properties on the paths in the graph. Essentially, whether they are open or flow information. You can think of it as an open path being a path where information flows, and a closed path where information doesn't flow, predictive information, if you'd like. So here's a classical example by Yuda Perl. Let's say we have installed in our house an alarm, and it goes off if there's a burglar or an earthquake with some probabilities, and our neighbor calls with some probability when they hear the alarm, and our neighbor Mary calls when they hear the alarm independently. Okay, so let's see the information flow in the independencies that we would expect intuitively. We would expect this path, which is a directed path, a causal path, to be open, information to be flowing. We would expect burglary to be dependent on whether John calls. Why is this the case? Well, when John calls, makes this more probable, which makes this more probable, right? But now, if we condition on the intermediate causes, information stops flowing, okay? So we would expect that condition on alarm, whether John calls or not, doesn't give us any additional information for burglary. Okay? Well, why is the case? Well, if we know the alarm is on and they call, doesn't give us information about whether there's a burglar or not, any additional information. Okay, so this type of paths, direct paths, are blocked only when you condition on the intermediate nodes. Let's consider these paths. This is a fork, a divergent path. Okay, again, when we don't condition on it, we expect information to be flowing, and a dependency. When John calls, makes this more probable, makes this more probable. But once we condition on the common causes, on the intermediate nodes, the information stops flowing, and we expect an independency. And now, here comes the, let's say, less intuitive part. Now we have a different kind of path which goes through a collider, two incoming edges. And, well, is it open or closed? Well, if I tell you there's a burglar in your house, does it make more or less probable that there is also an earthquake? It doesn't give you any additional information, presuming that burglars don't know when an earthquake is going to happen. But let's say now you're given that the alarm is on, you know the status of the alarm, and now I tell you that there is no burglary. Does it make an earthquake more or less probable? Makes it more probable, right? Okay, so there's an asymmetry here stemming from causality, and the asymmetry is that conditioning on colliders, and the same is true if you condition on the descendants of colliders, opens the path, otherwise the path is closed, okay? So putting everything together, and of course people have proved this, is that we have an open or a deconnecting path if we condition on every collider or one of its descendants, and we don't condition on the non-colliders, and then the path is open. And when we try to determine whether A and B given Z are disseparated, we consider all paths, and if all paths are blocked by Z, then they are disseparated, otherwise they are deconnected. Okay? So in this is the case where there's at least one path with information flowing, and here no path with information flowing. And the theorem goes that in faithful Bayesian networks, this separation holds only if and only if independence holds. So we check this in the graph, and this is what we expect to find in the data. This is what connects graph and data, all right? And now we have in our hands a tool to check the graph and see all the independencies that hold. And the question is, now we can find out from the graph the independencies, what's the solution to the feature selection problem. Okay, a note on faithfulness. What does intuitively, what does it mean? Now let's see this graph. Do we expect in our data to see dependence between sunscreen and melanoma? Under faithfulness, yes, because there are these two paths, right? And condition on the empty set, they are open. They are not blocked because they don't go through colliders. But what could happen intuitively in reality? It could happen. Well, sunscreen, of course, as we know, directly reduces the chances of melanoma. Okay, there is some negative association there. But putting also sunscreen makes people stay longer in the sun, which makes them get more melanoma. And it just could be the case that these two associations exactly cancel each other out, and in your data you see no association. Okay? So the faithfulness assumption is that this doesn't happen. That if you have a structure like that, you'll see an association between these two, and it's not going to be, you're not going to be so unlikely that associations are exactly going to cancel out. That is the major assumption of the algorithms I'm going to present. Okay, so what is now, putting everything together, the solution to the feature selection problem? Here's a network from the insurance domain that some expert created, and let me emphasize, we don't know in reality, obviously, the causal graph. In practice, what we have is data, and we can make questions to the data about some conditional dependencies, right? Okay, so we have the data, and we try to, let's say, predict the model of the car. What are the features that I should select to make everything else independent? What are they? Let's see. Well, you absolutely need the neighbors, the parents and the children of this variable, because you cannot deseparate them. You cannot block these paths. They're only one edge away. You cannot block them. These variables give unique information for prediction to predict this target. So you need to condition on them. You need to select them. If you condition on them, then paths like that open. Paths that go through a common child open. This is a path that goes through a collider, and we condition on the collider, so it's open. So, and you cannot block it if you condition on this any other way. So you also need to include the vehicle year. And for the same reason, you also need to include the mileage because it has this common, this path. And these are the only features that you need, and everything else becomes independent. Sorry. Okay, so basically you can prove that the Markov blanket, if you know the causal structure, the Markov blanket is the neighbors, or if you would like, the parents and the children of T, and the spouses of T, meaning features with a common child. Okay? That's all you need. That's the solution to your Markov, to the feature selection problem, if you were given the causal graph. Okay, there's a nice theorem that states that the Markov blanket is actually unique. It's a single unique solution in faithful distributions. And there is also a mapping of this to the taxonomy of features I gave before. Basically, the Markov blanket, these features, are indispensable. Anything connected to T with a path is redundant. You don't need it, but gives information in some context. Anything not connected to T is irrelevant, and there are no replaceable features when you have a faithful distribution and a unique solution. Okay? All right, so the algorithms will try to find this from the data without necessarily reconstructing the whole network. All right, what about when you have latent variables? Now, this is a very thorny issue. What happens? Well, let's see. Let's assume that mileage is not observed in your data. Then we cannot condition on this, but we do condition on the car values. So this path becomes open because this path, if you see here, goes, we condition on all colliders on the path. We don't condition on any non-collider, so it opens up, and we now need this variable too. And once we select this variable too, this path opens. So the Markov blanket here, we need to also include all nodes connected with what is called a collider path, a path that goes through observed variables that are all colliders. Okay, so it's a little bit more tricky. Now, what about if we don't observe airbag? Then this path cannot be blocked conditioning on the observed variables. So we need to include cushioning. And that's not a child anymore, but it is a child of make model in the network where you marginalize airbag, the unobserved variable. So again, and I don't want to go through the theory of causal models with latent variables called maximal ancestral graphs, but it suffices to say here that, again, the Markov blanket is all nodes connected with a collider path in the marginal network. Okay? So these theorems and this theory gives us a way to characterize algorithms and solutions and their properties. Yes?
This presupposes that you know where the latent variable is, but you know its place in the graph.
Yeah. No, if you know the graph, then you can, you can construct the marginal network and you know the Markov blanket. We'll try to find it from the data. Okay, but in order to trace what the algorithm is going to do, I assume I know the graph to see like what is happening. Okay, so here you see that causality is actually determine the solution to the feature selection problem and gives us an intuition what we expect to find. Okay, in the simplest case, no latent variables. It's the parents, children, and the spouses of the target. So it's intricately connected to knowledge discovery and causality. Okay, so now let's go and see some of the algorithms that are based on this theory. And here's the simplest algorithm called forward-backward search that was invented by statisticians as early as the 50s, but it was rediscovered in this context more recently. So we start with all variables in consideration, the remaining variables in consideration. We compute the p-values of all variables given the selected ones of all variables with t, and we select the variable with the minimum p-value, the one that has the largest dependency in some sense. And we remove it from R, and if it's dependent, if the p-value is small enough, we select it. Otherwise, we stop. Okay, so let's see a trace here of the algorithm. But before that, in terms of computational complexity, in every step, in every selection that we do, we need to compute the p-value with all other variables. If you have millions of them, this algorithm is not going to scale very well. So in order to predict make model, you compute p-values from your data. Okay, and let's say the minimum p-value is by other car cost, and then rugged auto, and so forth, and these variables enter. And at this point, the algorithm is going to stop because if you can check that everything else is independent of all other, if you take any other variable, all paths to make model are blocked by the selected ones. Now, in this case, we also have a false positive, which is this one. It's not in the Markov blanket, but we selected it. So we do a backward selection, and we try to remove variables that become independent when you condition on all the selected ones. Okay? So you condition all the selected ones, except, of course, the variable v, and then you check whether v becomes independent, and you select, now in the backward phase, you select the variable with the maximum p-value, your safest bet that it's really independent. Okay, and if you do that, first of all, you need to compute p-values with all the other selected variables, which is not that bad usually, and you will remove all false positives. And yes?
So in the forward phase, why did you, would this assume that you know the graph structure?
No, you just compute p-values. P-values. You check in your data, and you run a conditional statistical test whether T has information, V has information for T once you're given S.
So this has nothing to do with the structure of law. And so basically what
No, I use a structure to understand what I can possibly get from this algorithm. Look, this is the algorithm. Does it use a structure anywhere?
at least the forward part does not.
Oh, neither the backward. All the access to the data is by computing p-values. All the algorithms just compute p-values. You don't know the structure. I'm just giving you an example, though. If you knew the structure, what could happen? Okay? So now, if you check every other variable, let's check this variable. It has this path, has this path. This variable. It has this path to make model, this path, and this path, and many others, but they're all blocked. For example, this path is blocked because we condition on anti-lock. This path is blocked because it goes through a collider, and we don't condition on the collider. Plus, we condition on many other non-colliders. And this path is blocked because of risk aversion. So it will be removed by this procedure. I'm using the graph just to know what I expect to see in the data, what I expect to see removed, for example, by the algorithm. Okay? So it's a very simple algorithm, and it's suitable when one has the statistical power to condition on all the selected features. If you expect to select 100 features and you have enough sample size to condition on all of them, use it. It's pretty good. Now we can also prove theorems that if you have perfect tests of condition dependence, you don't have any statistical errors, it will return the Markov blanket of T in distributions faithful to a Bayesian network even when you have some features latent. Okay? So nice theoretical property. Of course, the complexity is not that good because it's n times s, where n is the total number of features and s is the number of selected features in terms of the number of tests that you will perform. Okay, now recently, yes? Yes, you need to correct if, I mean, the correction just increases or decreases the alpha level here. Okay, it's not that easy to correct though. But there have been efforts, but you're right. Okay, now in recent work, we thought about like improving this algorithm by interjecting here this step where you actually drop from R anything that becomes independent, given the selected variables. And this filters out variables very quickly. Let's see why. Let's run the algorithm. So again, let's say in the first step, we will condition on the empty set. We have nothing, selected nothing. And if I knew, knowing the graph, I expect to drop and remove this variable. Because this variable, the only paths that it has to make model go through colliders. Since we don't condition the colliders, we're going to throw it away, filter it out. And next, let's say we select this one, and nothing gets dropped. Then we select this one and condition on both of them. All the paths to other car are blocked. It's removed. Let's say I select this one next. And now all of these become independent and are dropped and so forth, if you check. And actually, in a very large network, a lot of features will be dropped at each point. And now let me check, like, what are in the forward phase, again, we have this as a false positive, but now I also have two false negatives. Why? Because I removed them because before I inserted the children here to condition upon and make them dependent. So I have two false negatives, which is not good. But on the other hand, I improved a lot the complexity because at each step, I only check the p-values with the remaining features. The ones in red were dropping at each time, giving me a speed up. So, well, it has some benefits, it has some disadvantages that you actually have some false negatives, but we can fix that by noticing, by running again the same algorithm in a loop, as long as, and each time starting with the previously selected features and reinitializing the remaining features to be all features, no reds, and giving them a second chance to enter the selection. And this time, we're guaranteed that we're going to have the children and the parents, but the children is more interesting. The children are going to be selected. So conditioning on these, all of these will be dropped immediately. And these Markov blanket variables will have a second chance to enter. And then this is going to be dropped. And actually, for Bayesian networks, you can prove that running this, the previous algorithm just twice, and then the backward phase is going to give you the Markov blanket. If you have like more distributions faithful to a Bayesian network with latent variables, then you may need further repetitions. Okay, so this algorithm is again suitable to run it on the same situation, and the theorem says that if you run it, if you run the forward phase a second time, you give features a second chance, then you're guaranteed the Markov blanket in distribution faithful to a Bayesian network. If you run it as long as you keep adding features, then it's gonna, you're going to get the Markov blanket in distribution faithful to a Bayesian network, even in the presence of latent variables. And in practice, this is much faster. Yes?
So what you're saying is that the upper bound of K is 2 for Bayesian network.
For Bayesian network, yes.
So
You just need 2.
does it have proof?
Yes. That's why it's a theorem.
Okay, so it's in your paper.
Yes. Okay, so we tried this in a bunch of data sets here with varying sample size and varying variable size. Okay, and here are some summary results. Here's the AUC difference with a baseline forward-backward selection. Here's the relative number of selected variables. And here are the medians of the results for when you run it just once or an additional extra time or as many as it takes. And you can see that basically there's no difference in the quality that you get, but you usually get fewer variables selected. And if you check the times that it takes for when you run it a single time with a dropping, it's 1.5 order of magnitude faster, okay? And the difference also really becomes larger for larger variables, feature sizes, data sets. We then compared with Lasso, which is very common algorithm to use. Here's the accuracy difference between the two algorithms. Here's the AUC difference. And you see basically these are the medians. There is no difference really between the algorithms. Now, mind you here that Lasso was restricted, both algorithms were restricted to select the same number of variables, okay, to make it fair. So there's no difference in performance, basically. Okay, so the previous algorithms are, the previous algorithm is fast, it scales up to the number of variables, but it conditions every time, the p-values here condition on all features, all the selected features. And if for small data sets, this is not gonna work. So we have algorithms that we restrict the p-values to condition on subsets of size only up to k, maybe 2 variables, 3 variables, no more. Even if you're going to select 100, you're a strict condition on only 3 variables, let's say, all right? In this example, k equals 2. Let's see what we're going to get. And the idea is that, again, you select a variable to include in the selection in S. How do you select this variable? Well, you now condition on all subsets for a variable of size up to k, and you take the maximum of them. And then you select the variable that has the minimum out of these maximum p-values. Now, why this is a reasonable heuristic, I'll explain a little bit better, but this is our heuristic. And anything that becomes independent condition on some subset of the selected variables, you drop it, all right? And the algorithm continues like that. So let's see what we're going to get. Can we get false positives, false negatives? What features are we going to select in every case? Initially, we haven't selected anything. We condition on the empty set. And this variable here is going to be independent, and we'll remove it. Let's say we then select this one and this one. This one is going to be dropped because condition on just one variable, it's blocked. The path is blocked. This one, all these variables will go away. So again, you see that a lot of features are filtered out quickly, and you don't need to keep computing p-values. And this one. So this is an example trace. Now, this, if you have k equals 2, if you only restrict yourself to k equals 2, to condition on two things, all these other variables will not be blocked, will be dependent, and will be selected to as false positives. Why is this the case? Well, let's consider medical cost. This is one path. This is a second path. This is the third path. And you need to condition on simultaneously to block them all. You need to condition on three things. All right? So if you restrict yourself to conditioning on two because you don't have sample size, then this is also going to be selected and appear as a false positive. Okay? So about the complexity here, we condition on all the remaining features not dropped, so that's fast. But for every new subset of the selected variables of size k. All right. Now, there is a weird case where actually this may return false features that are not parents or children. But the short story is that we can fix it theoretically, but in practice, it's not worth the computation. Yes? Pardon me?
Two questions. So one is the outcome variable insurance?
No, the outcome. No, I'm trying to predict the make model. That's my target. What is the meaning of these variables?
Yeah. Well, you said it was featuring policies, right? So it's kind of airbagged and then how many airbagged and
Right, and here's whether they got an accident. And they created this network because they were trying to predict the medical and liability and other costs. But here, let's say we know the costs, and I'm just trying to guess the model of the car, all right? Just for example purposes. Because I didn't want a variable that we know has no effects and would make things much simpler. Yes?
When you're picking the variables to condition on, right, you're picking them
Yes.
partly at random.
No, it's not at random. I condition on all subsets, I get the p-values, and I record for each variable the maximum p-value. And then, out of all these maximum p-values, I take the variable with the minimum maximum p-value. Pardon me?
It's a greedy approach.
Well, yeah, all these algorithms are greedy in some sense. Okay, so basically, the theorem is, this is an algorithm that is suitable when you don't have enough sample size to condition on everything. You only can condition up to k variables. And we can prove that this algorithm is going to return, if you have at least large enough k, the neighbors of t, the parents and the children, okay, in any distribution faithful to a Bayesian network with latent variables. Okay. Now, this is the complexity. So if you select 100 variables in k equals 3, it's like, 100 to the third tests in the worst case, but it's linear to the number of variables. And usually in practice, we found that 3 and 4 suffices for excellent results. Now, a little bit about the heuristic. we discovered a nice interpretation in 2008 that it actually minimizes a bound on the false discovery rate of the neighbors. And it's pretty effective. Okay, so this algorithm and variance have been thoroughly tested against many other feature selection algorithms in the literature, in many data sets, different types of tasks, particularly in a series of papers against binary classification tasks, multi-class classification tasks, time to event or survival analysis, and also recently for temporal data, where you actually try to predict a trajectory given other trajectories. And the bottom line is that MMPC always performed equally well or better than its competitors, often returning more parsimonious models and fewer selected variables. On the binary classification task in 2010, it was tested against 43 other algorithms of variance, including least angle regression, very similar to Lasso, random forest variable selection, recursive feature elimination, and others in 13 data sets. In the same year, we tried it for very high dimensional data, omics data, gene expression data, where you try to predict the survival time, and it fared very well. In 2010, again, we equipped the algorithm with a condition dependence test for multi-class targets and ordinal targets, and compared against Lasso and other algorithms, and fared again very well. So there's been a body of work that is gathering that these algorithms actually scale up and give you quite good feature selection. Now, an extension of the previous is called SES, that finds multiple solutions. And recently, just submitted, we equipped it with a condition dependence test for finding, for temporal data, time course data, for example, gene expressions over time, and tested on several data sets in the public domain. It's interesting that in this case, Lasso doesn't give you a convex problem, okay? So the problem with the L1 norm minimization with time course data is not convex anymore, and Lasso doesn't really scale up. At least the implementation is available. I don't know if it's a theoretical problem, but I think it is. But SES does scale up quite well. All right, so putting all my experience in feature selection together, I would give the following advice to practitioners that, first of all, yeah, Lasso is usually pretty good to try if you can try it. If you have very few features but large sample size, just use exhaustive search. There's no need to run any algorithm if you have 10 features. If you have large sample size but few features, there are some recent exact methods. If you have large sample size relatively to all available features, just use backward search. Otherwise, use forward-backward with early dropping. And if you have small sample size, use MMPC that I described. Also, we have some statistically robust tests that we have devised that are pretty fast. And after the feature selection, don't use use your favorite robust and high-dimensional classifiers. They don't trust, for example, if you use Lasso, why not use SVMs afterwards? Lasso is a linear method, right? Okay. We have implemented all that in the MXMR package. And you can see here we have a bunch of condition dependence tests that we have implemented. So you can run it on continuous variables, categorical, proportions, counts, zero inflated counts. Use it for survival and time to event analysis, ordinal data, and case control data, and so forth. With the same algorithms, just you plug in a different condition dependence test. Okay, and in the end, I left, if I have a few minutes, to describe a work that's been submitted yesterday. So it's really, really fresh. For big data, how do we scale this up to big volume data? And when I say big data, it's data that doesn't fit in your desktop. You need maybe a cloud to fit the data. So the problem there is like, how do we make the computations, and the computations we use is the p-values, okay? How do we make the computations local to the data partitions? Your data is distributed all over. You want to make computations local without the exchange of messaging too much. And since you have a lot of sample size, it would be good to stop computations as early as possible when you determine in some intelligent way that, okay, I've seen enough to make a reasonable decision. So we devised this algorithm, which is joint work with other colleagues very recently. And the trick we use to make computations local is to use meta-analysis technique to combine local computations to global statistics. So we communicate only statistics, not the data, and asymptotically also you get the same answer. And we use the early dropping heuristic again, same as the one I described. And two new heuristics, early stopping, that essentially we perform a bootstrapping test to decide that we've seen enough to know that the feature is not going to be selected in this iteration. It's not going to be the winner, so stop computing p-values on this feature. And the early return, which essentially if you have several equally good candidates for selection with very small differences, you don't need to go through another 10 million samples to determine really which one is the best. You just select one right now. And so it's highly parallel, low computation cost, scales to many variables, and sublinearly actually with sample size. Here's some graphs about how it scales. This is the number of sample size. You see, when you have 5 times the sample size, the execution time doesn't go up 5 times, it goes less than that. When you have 5 times the number of features, again, the execution time doesn't take 5 times as much, it takes less than that. And it parallelizes not with a theoretical optimum, but it parallelizes linearly with a number of machines. Here's a comparison with on real data sets ranked by number of variables ranging from small ones, 18 variables, to data sets with 30 million features. Okay? And we compare against the forward-backward search, where the condition dependence test is parallel. We used Spark's parallel implementation of logistic regression to make a test that is parallel. Univariate feature selection, where you rank the features according to p-value and you take the top k, but again, computing the ranking is done in parallel to be fair. And an algorithm by some people in Google called SFO. And there's no need to look so much in the numbers. These zeros tell the whole story. The zeros means that the algorithm's bombed, or after the timeout didn't return anything, not even a single feature. Okay, and you see that in the large data sets, basically all competitors just bomb. In the cases where they all return something, the accuracy is pretty much the same, so they all have around the same quality of selection, essentially. Okay, I'll skip that. And in conclusion, I hope I argued why feature selection is a main tool for knowledge discovery, and that it's really connected to causality. And causal models really help us understand the problem, define the problem in a correct way, know what to expect, and in a non-parametric way. The assumption was faithfulness, which is not a parametric assumption, like linearity, for better or worse. And by using this theory, it inspired us to design algorithms that, for which we can prove the theoretical properties, whether they're going to asymptotically find the Markov blanket and in which distributions. They're applicable to any types of data as long as you plug in the right condition dependence test, and there are plenty of them around. They scale up to big data. They have competitive predictive performance. Now, as I said, we're working on extending them to finding multiple solutions. The solutions have an intuitive causal interpretation. So for the simplest case of Bayesian networks, the solution is the parents of what you're trying to predict, the children, and the spouses. And if you want implementations, you can download the R package. Now, I would really like to thank my group in University of Crete, but particularly Yorgos Borboutakis, who is this guy smiling here, and Vincenzo Lagani, making our team international because he's Italian. And of course, the funding we received over the years, the colleagues I worked with over the years, and the hosting institutions, more recently, University of Crete. Here are some references. I'd like to thank you very much for your attendance. Hope I didn't take too much more time. I'll cut it from our other talks. Thank you.